is basic identities under Boolean algebra. So, Boolean algebra is a branch of mathematics that deals with operation on logical values with binary variables. It is used to analyze and simplify the digital circuits or logic circuits. It uses only the binary numbers which is 0 and 1. And it is also called logical algebra. This type of Boolean algebra was developed by George Boole, an English mathematician. So he has two major works, that is the mathematical analysis of logic and the laws of truth. So we have rules to follow in your Boolean algebra. So first, we have a variable use can have only two values, that is either 0 or 1. Binary 0 for low and binary 1 for high. Complement of a variable is represented by an overbar. So a complement of a variable A is represented as E bar. Logical ORing of variables is represented by a plus sign between those two variables. For example, if we have variables E, B, and C, if we have to use OR, it can be written as E or B or C. Logical ANDing of variables is represented by a dot between those variables. So if we have variables A, B, and C, since we are using AND, it can be written as E dot B dot C or just EBC. So these are your Boolean laws. First, we have the commutative law. If we have AB, that is the same as BA. Or if we have E or B, that is the same as B or A. So commutative law states that changing the sequence of the variables does not have any effect on the output of a logic circuit. The second law that we have is the associative law. If we have quantity E and B plus quantity, then and C that is the same as E and with quantity B and C. Or if we have quantity E or B, then or C that is the same as E or quantity B or C. So associative law states that the order in which the logic operations are performed is irrelevant as their effect is the same. Then we have the distributive law. If we have A and with the quantity B or C, it can be written as AB or EC. Next, we have the annulment law. Using the AND, if we have A and 0, that is equivalent to 0. Using an OR, if we have E or 1, that is equivalent to 1. And we have the identity law. Using an AND, if we have E and 1, that is equivalent to A. Using an OR, if we have E or 0, that is equals to A. Then we have the idempotent law. If we have E or A, that is equals to A, or E and A, that is the same as A. Then we have the complementary law. If we have E and E bar, that is equivalent to 0. Or if we have E and or E bar, that is equivalent to 1. And we have the inversion involution law, or the double negative. If we have E double bar, it is equivalent to A. Then we have some important Boolean theorems. This is what you call the De Morgan's theorem. So theorem number 1, if we have A none with your B, or that is AB with a long bar, it can be written as E bar or B bar. So it means that if we have to break this bar between the two variables from the sign of an AND, it will change to an OR. Or vice versa, if we have to join these two variables from the sign of OR, it will become an AND. So the left-hand side of this theorem represents a NAND gate with inputs A and B, whereas the right-hand side of the theorem represents an OR gate with inverted inputs. So if this is your AND or NAND, we have A, NAND B. If we are using the OR but with inverted input, that is E bar NOR or B bar. To prove that they are the same, so we have to use the truth table. We have input A, B. Then for A and A NAND B, that is equivalent to 1, 1, 1, 0 for your input from 0 to 3. Next, we have to get the complement of A. So we have 1, 1, 0, 0 from 0, 0, 1, 1. And also we have to get the complement of your B. That is 1, 0, 1, 0 from 0, 1, 0, 1. So if we have to OR this E bar and B bar, so we have the same output with your E NAND B. So this expression is the same as this one. Theorem number 2, if we have an A nor B, it is the same as we have E bar and B bar. So we have to cut this bar between your two variables from the sign of an OR, it will change into a sign of an AND. Or if we have to join these two variables from the sign of AND, it will become a sign of OR. So the left-hand side of this theorem represents a NOR gate with inputs A and B, whereas the right-hand side represents an AND gate with inverted inputs. So this is our NOR gate with input A and B. Then if we have to get the equation of your NOR, that is A NOR B. If we are going to use the AND gate with inverted input, so we have E bar and B bar. So to prove that they are the same, so we have to use the truth table. We have input A and B, so your combination is from 0 up to 3. So we have to get your E nor B. So for your A nor B, so we have an output of 1, 0, 0, 0. So we know already that if we have input 0, 0 in your NOR, it is equivalent to 1. If one of your input is a 1, you have a value of your NOR equivalent to 0. Then next, we have to complement your A, that is 1, 1, 0, 0, and B, that is 1, 0, 1, 0. Then using an AND, we have to AND your E bar with B bar. So therefore, your output of your NOR is the same as your output of your AND with inverted input. So we have to verify the equation of an XNOR gate. So we know that an XNOR gate, we have this circuit, a combination of your AND gate connected to a NOR. One of the input of your first AND is connected with an inverter from A, and the other input of your second AND gate is connected with inverter from B. So if we have to get the equation of your Y, that is equivalent to your E bar B nor E B bar. So we have to use your De Morgan's. So we have to cut this one, or we have to break this bar. So we have now equivalent to E bar non B and with A non B bar. Then again, we have to cut this between your variables. So that is equivalent to you have now a double bar or b bar and with a bar or b double bar. Using double negative, so it will become an a or b bar and with a bar or b. Then we have to distribute. So we have a bar or a b or a bar b bar or b bar b. Applying your complementary law, so that is equivalent to ab or e bar b bar. So this is now your equation for these circuits, a circuit that is equivalent to your XNOR. Another one, if we have to verify that your E and B or B bar is equivalent to E or B bar. So first, we have to multiply 1 in the second term of your equation. So therefore, that is AB or B bar times 1 or an 1. Then, using the annulment law, if we, that is, we have a result of 1. So we have AB or B bar, then it is and with your A or 1. So this is your annulment law. Since the output of this one is equivalent to 1. Then we have to distribute your B bar to the quantity. So this is now equivalent to AB or EB bar or B bar. Then we have to factor all A. So we have now A and with the quantity B or B bar, then or B bar. Using complementary law, so that is equivalent to 1. So this is equals to 1 using complementary law. And using your identity law, so that is equivalent to AB bar, E or B bar, that is the same as your E or B bar. So this equation is equivalent to this one. So another, if we have to verify that A, B bar or B is the same as E or B. So we have to multiply 1 to the second term. So we have now A, B bar or B with your 1 and with 1. Using your annulment law, the one that we have is equivalent to E or 1. Then we have to distribute. After distributing your B to the quantity E or 1, we have to factor out all A. Then B bar or B, that is using complementary law, it is equivalent to 1. And using your identity law, your E and 1 is equals to A. Therefore, E and or B the same as E or B. So this equation is the same as to your right hand side. So that's all for your lecture number 1, which is the basic identities of your Boolean algebra.